Hi, this is Kevin Trainer. Welcome to my lecture for Chapter 2 of the John Zelle Python Programming 3rd Edition book. And Chapter 2 is about writing simple programs. For some reason this time I'd like to give a little bit of a preview by going through the objectives that we're trying to achieve. To know the steps of an orderly software development process. This is especially important for new programmers who really haven't been part of that process. Next, to understand programs following the input process output pattern and to be able to modify them in simple ways. Well, that's good. I think that's a good pattern. It's one that I learned long ago, and it still serves me well, so I think you'll like it. Next, to understand the rules for forming valid Python identifiers and expressions. So these are syntax rules for Python, and we're going to want to get you to the point where those are pretty much second nature to you. And we do a lot of that by the examples that we show, but we're going to go over some of the more formal rules. And last, to be able to understand and write Python statements to output information to the screen, assign values to variables, get numeric information entered from the keyboard, so we're going to get some input this time, and to perform a counted loop. Okay, those are all good things. Now, we did a few of those things in the last chapter, but we didn't really talk about them too much. So we're going to talk about them some more here. What the question comes when you're about to start to write a program? What's this like? Is this like building a rocket ship? Is it like feeding a baby? Is it like mowing the lawn? What's it like that I've already done? Okay. And I think that if you're a person who's written sort of a prose-based business reports, or even term papers or things like that, that writing a program, kind of organizing what it's supposed to do, and then constructing it, and then checking it over to make sure it's right, and all that kind of stuff. It's not terrifically different than the writing process for a person who's put some thought into writing approaches and is willing, to edit and change their writing, and wants their writing to be organized in a way that is sort of intuitive for the reader to find the parts of it. Okay? Now, in both of these processes, what we try to do is we try to break down what we're trying to communicate, in one case to the reader and in another case to the computer, and we try to break it down into parts and address those in stages in order to be able to do it in an orderly way. So the first thing is that we analyze the problem. We figure out exactly the problem to be solved. We try to understand it as much as possible. Now, in the context of being a learning programmer, problems typically come to us as classic word problems that we remember from grade school math. We've got two trains that are approaching each other or a class of 45 people goes somewhere. It's typically a word problem. Okay? Now, Is that how things happen in the real world when we're doing this for our day job? No. We go talk to people about opportunities to help them get their job done. And they talk about their job and what kind of help they'd like. They talk about how they do their job right now in the absence of the program solution that we're going to produce. And we kind of talk through it with them, and then we come up with some kind of analysis of the problem, and we write it down using some techniques. There are a lot of techniques out there. The ones that are very popular now, there's one from Agile software development called user stories, okay, which is a very lightweight, very summarized way of telling a story about how a user is going to use our software to get their job done. Okay? So maybe someday we'll learn how to write, how to document requirements with things like maybe user stories. But we're going to try to learn to do is we're going to try to learn to express the analysis of the problem in kind of the same way it gets expressed in the textbook. If you go to the end of the chapter and you look at the exercises, each of them is a word problem. So what we're going to do is we're going to reduce it to a word problem, and we're going to kind of organize it from there. That's a little artificial, but we don't have real people to lend you, so that's how you're going to get it in the short run. The second step of the process is we determine the specifications. We describe exactly what our program will do. Some advice from the author: don't worry about how the program will work, but what it will do. Includes describing the inputs, the outputs, and how they relate to one another. So there's a couple of, I think, important ideas in here. And one is don't get ahead of ourselves, okay? As soon as, when we're learning how to use a particular tool, as soon as a person begins to talk, we have this kind of vision going through our mind of us using the tool, right? So we have the saying that if you have a hammer, every problem looks like a nail. Okay. And one of the problems of getting too detailed about exactly how we're going to solve things before we really describe what we're going to achieve is that we can waste a lot of effort. Okay, we can maybe not completely understand what we're trying to accomplish, and then already kind of go off to start to implement it. And of course, if we ever discover that we're solving the wrong problem, then we're probably going to have to throw away that code. So one of the things that we tell people is to describe things generally at first, okay, and then to get more specific until we're at the point where we can just turn it into code. Okay? And some of the early descriptions, something like maybe a word problem description, or in a little while we're going to see something called pseudocode. These are even things that we could go back to the potential users of our system and say, okay, well, I've done some thinking about what you told me, and I think that this, in say the word problem write-up, this kind of describes what we're trying to solve. Do you agree? And you get some feedback, and you might find out, oh, I misunderstood something there. And later on, when we learn how to do pseudocode, you might say to that kind of person, I've put together a rough outline of how I'm going to solve your problem, and I just want to walk through it with you. Do you have a couple minutes? And they might say, yeah, and you might be walking through it with them, and they'd say, oh, Kevin, that's right, except you've misunderstood me in this part here. So one of the good parts about going at the solution in a kind of stage by stage, this is a process that some people call progressive elaboration, is that early on, the problem is expressed in ways that the potential users can understand. And it's easier to take those kinds of expressions of it back and show it to the users and say, am I close? Did I misunderstand something? And really get some helpful feedback. Okay? And then the nice thing there is that you haven't built the thing yet. Okay, you've built some word processing document, but you haven't actually built and tested the code. And so these kind of early expressions keep us from getting ahead of ourselves, and they're also better for checking with the end users of our product than the actual programs themselves would be. The other idea here that I think is really important is, there's a lot of kind of patterns that we talk about in programming. And one of them is called input, process, output. Okay, and so typical computer programs get their input from somewhere. The easiest thing for us in the short run will be from the keyboard. And they do some processing. And then when they're done with their processing, they create output that the user consumes and goes, they do their job or they go about their personal life and enjoy it. Now, there are some programs, the kind of early ones that we're going to learn how to write, they're kind of like 3 stages and you're done. You get your input, you do all your processing, you produce all your output, and then you're done. Okay? As things get a little more complex, though, there might be a problem that we would solve by repeating that process. So we get a little bit of input. We do a little bit of processing for that input. We create a little bit of output. And perhaps we ask the user, are we done yet? No. Well, get a little more input. Did a little more processing. Do a little more output. Are we done yet? So we go around in a loopy kind of a way until we're done. So this sequence of input, process, output, either in just one shot or kind of a looping variety of it, is a great way to think of way to organize computer programs. It's called the input, process, output pattern. Okay? So once we kind of understand what we're trying to solve and we've kind of thought about it in terms of maybe patterns that we understand, we want to come up with a design for the program. Okay? And if you remember chapter 1, we had a kind of a high level design for the program. We were going to put our highest level code into a function called main, and then we were going to call it with a single invocation or call to main. Okay, and we did also see last chapter that for programs that do appreciable work, it's not useful to put all the working code into main. That we tend to factor out subparts so that in a more typical larger program, instead of main containing all the code, all the working code, it really creates a high-level summary. Okay, so now we're going to come up with a design. So we formulate the overall structure of the program. All of our programs are going to have that main kind of approach, but we have to think about what maybe subparts of main would be. This is where the how of the program gets worked out. And we develop our own algorithm that meets the specifications. Now, algorithm is an interesting word. It's an approach to solving the problem. We talked about that in chapter 1 as well. And the word that I like for it is recipe. So it's a recipe for solving the problem. And recipes that we use, say, for cooking or for baking, are usually expressed in terms of the actions and the objects that we use for cooking and baking. Okay, so here it's going to be a recipe for solving the problem, and it's going to be in terms of computing-ish things. And one other thought to think about here when we go to create the design of the program is that computer programs, I think, as we've seen so far and will continue to see, they don't solve problems like humans do. Okay, so humans tend to use a lot of intuition, and they use a lot of kind of visual understanding. So one of the classic kind of comparisons I like to make is when we have a list of things and we want to sort them into order. Most humans, if you give them a list of things and you want to sort them into order, they'll kind of look at it and go, well, it's pretty close to in order now. I have to pull this one from the bottom and put it up towards the top and move this one down. Then they kind of eyeball it and they say it's, well, I think that's it. I think it's in order now. Whereas to solve that problem with a computer program, you don't get the benefit of that kind of eyeballing. And so computers are not as intuitive or as visually intelligent as humans when it comes to solving problems, but they're lightning fast and they never get bored. And so the design we would come up for sorting a list into order is more monotonous than the way that a human would do it. But it's a good solution for a computer. And what we generally do is the simplest thing, I think we'll learn this before we're done. There's this approach called the bubble sort. So you start at the first item, and you assume that it belongs there, that it is the one that comes first. And then you go through the second, through the last, and you compare every one. And if the one you find should go before the one that you're working on, in this case the first one, then you swap them, and then you begin again. So is that the way a human would do it? No, that's really it's too rote. It's too mechanical. It's too boring. We would lose interest long before we were done. And there are some, there's some tricks to sorting. The bubble sort is the most intuitive approach to sorting that's done. There are some tricks that you can learn to do for sorting. One of the nice things is that languages like Python have functions that are already built that will sort some of the data structures that we build, so that we don't even have to tell them how to sort it, just that we want to use the sort on a particular data structure. So I got on a bit of a tangent there, but my point is, when we create the design, it has to be one that is of the ilk of the way we create designs and algorithms for computers to solve problems, not the way that we would do it if we were doing it in our kind of very visual, very intuitive kind of human problem-solving way. Then we have to implement the design. So we want to translate the design into a computer language. In this course, we're going to use Python. So the question is, are we going to do that directly? So are we going to go from some just kind of expression of the design that's probably in maybe narrative prose? It's word problem-ish, okay? Are we going to go right from there to Python? And we're going to say, well, not so fast. We're going to learn about an intermediate stage called pseudocode. Okay? But we're not going to talk about it quite yet, apparently. Okay, so once we've turned we've gone to pseudocode, which we didn't talk about yet, but of course I did. And we've turned it into Python, then we're going to test and debug the program. And one of the things I really like about this chapter and the way that the author talks about it is that for this author, and certainly for me and professional programmers everywhere, testing is not an afterthought. Testing is a big part of the main activity itself. So for instance, if you came to me and I said, oh, I need help, I need you to put together a problem to solve the problem. You put together a program to solve the problem, and you came back and said, well, Kevin, I wrote the program, here it is. And if I said, well, did you test it? And you said, oh, no, it's good. It doesn't really need to be tested. I would say, well, you don't really know this activity yet. Okay, everything needs to be tested, and it needs to be tested extensively. What we want is tested software. Now, that's not to say that there could not be latent errors that we did not discover, that kind of stuff. But generally, a complete job includes the testing. And when we're testing, we sometimes get wrong results. You'll see that we get programs that don't even give us results. My old friend Dan Hall used to say you can get one of three things. You can get the right answers, you can get the wrong answers, or you can get no answers. Okay. And so getting through problems that you find when you're testing is called debugging. And errors in programs are called bugs. And there's a really good story about why they're called bugs. And early computers and one of the mothers of early computing, Grace Hopper. And if you could look that up, I think it would be entertaining. But we do call them bugs. And the last point here, your goal is to find errors. So try everything that might break your program. There's a really famous programming expert who I read in my early days, and his point of view was the purpose of testing is to discover errors. And he even went so far to say that a test that it discovers an error is a successful test. And your last test, where you don't discover any further errors and you decide that you're done, he described that as an unsuccessful test. Now, that's not how people talk about things in common everyday language, but that was a great kind of a point of view. So professional programmers, they see testing as part of the process, and they want to, when they find an error in their code, they consider that a success. I mean, they don't get all down about it. They go, oh, I found another error. Let's get that fixed. Okay, so we test and debug the program. And then we maintain the program. Okay, so why do we have to maintain a program once it's been tested? And it's often said we put them into production. Well, two things happen. One is accidentally we did not discover all of the errors. So we call these latent bugs. These are bugs that were there, but we just didn't have the foresight to find them. Well, they turn up. People are using our program, and they put their input in, and they look at the output, and they go, that can't be right. So they bring it to us and said, I think I found a bug. And we say, okay, we'll investigate. Okay, so part of maintenance is fixing bugs, or investigating bugs and going back and saying, this was an apparent bug, but this is actually the way the features are supposed to work. There's nothing to be fixed. The other thing that happens is that the requirements that we're solving, they change over time. There's this kind of general feeling. There was an author who wrote a book, probably 30 years ago now, called Future Shock, where we were talking about the idea that the rate of change in our society has accelerated. And I think most people really think that's true. And so what happens is that as things change in the world, the problems change. Okay, and when the problems change, then if we have software that's going to solve the new version of the problem, well, then we need to change the program. So the changing the program to respond to changes in the requirements, and changing the program in order to fix recently discovered hidden bugs, that's what we do when we're doing maintenance. Okay, so here's an example program. It's called Temperature Converter. And we're back to math again. And one of the reasons that computer science authors like math, I think there are two reasons. Reason one is that they all were math majors. Okay, that's an exaggeration, but they all like math. They have a real affinity for it. Okay. Two is that some of these problems they believe are easy for everybody to understand. So they think, well, we went to grade school and somebody explained to us that there are two temperature scales, Celsius and Fahrenheit, and there's a formula for converting between them. And maybe not everybody remembers exactly what the formula is, but they have an approximate idea. So they want to give us a problem that we don't have to learn a lot before we have to go solve. So the temperature is given to us in Celsius. The user wants it expressed in degrees Fahrenheit. So the specification, the input, this slide has a typo, I see now. So it should say that the input is the temperature in Celsius. The output is the temperature in Fahrenheit. And the process is that the output equals 9/5 of the input plus 32. Okay, so yeah, that last statement, if it were kind of parallel to the two before it, it would say that what we have down here on the last of the bullets is a description of the processing. But what they've done is to, it's kind of write it in code, but that's the process. Okay, so what would happen if we kept to the model input, process, output? Well, we would get the input from bullet 1. We'd do the process on bullet 3, and then we would be ready to produce the output on bullet 2. Okay, so I might have organized this slide a little differently, but you get the benefit of both worlds when you get to hear what I have to say about it. So here's how we might go about the design. Okay. First of all, the only real kind of pattern that we have talked about in how to organize programs um, in the chapter so far is input, process, output, and he uses the acronym IPO as a shorthand for that. So if we're going to do that, so we're going to, in terms of input, process, output, we're going to do input. We're going to prompt the user for input, Celsius temperature. Then we're going to process it to convert to Fahrenheit. And he's giving us something that looks pretty close to Python code. It's not exactly proper Python code, but it's close. It's saying that the Fahrenheit temperature is going to be calculated as 9/5 times the centigrade temperature, which we already got, plus 32. And then we're going to output the result by displaying it on the screen. Okay, so this conversion, this kind of converter thing, there are a lot of problems that are converter problems, and they fit really well into this a pattern of input, process, output. So it's pretty easy to see how the design is going to work. But here's where we say, oh, look, before we go right to code, let's not be too much of a hurry, okay? Whenever we're going to write more code or more complex code than we're used to doing, one kind of half step that's a good step is going to pseudocode. So what is pseudocode? So pseudocode is precise English that describes what the program does step by step. Using pseudocode, we can concentrate on the algorithm rather than the programming language itself. Okay, so when we say it's precise English, okay, it's precise in the following way. It's a little closer to the language a computer understands. Okay, just the kind of things that we're talking about, of like inputting things or outputting things or calculating things. So we have like the nouns and the verbs that we need in pseudocode, but it's not as precise. The syntax, the format, it's not as exacting as a Python interpreter would be, or say a Java compiler would be. Okay, so what we're going to do is, in this pseudocode kind of half step, we're going to try to come up with an expression of the program design that we can see, yep, that's going to work. And then when we get it just the way we want, only then are we going to translate it into Python. And again, two advantages here. One is, if you're going to keep changing it around, you're going to save time in the long run. Okay. And two, it's probably easier to take the pseudocode back to our user base and show it to them and have them recognize it as an English expression of the problem rather than, you might take a Python program back to the users who you're writing this for, and they might say, well, Kevin, I don't know Python. But pseudocode is English-like enough that you could show it to them and walk them through it, and they might not be as put off by it. So that's another advantage of inserting this pseudocode step as a way of expressing your design before you turn it into Python code. So let me see if I can get to the next slide. It just doesn't seem to want to be coming. Okay. So here would be the pseudocode. Okay. First, input the temperature in degrees Celsius. Call it Celsius. Now, when we say call it Celsius, we're saying that we're going to have a variable with that lowercase Celsius name. Calculate Fahrenheit as 9/5 times Celsius plus 32. Okay? Now, in the last chapter, I think I mentioned that there are rules in programming languages for these order of operations, but this is, to the casual reader, ambiguous. Do we take 9/5 of Celsius plus 32? No, we don't. We take 9/5 times the Celsius and then we add the 32. So in my estimation, especially in pseudocode, but in Python code for sure, I would want to make sure that you had another set of parentheses around this to make it clear how you were doing the math. And then we output the Fahrenheit. Okay? Now, where would this go in our program? Okay, well, when we created our program, it would go into main. Okay, we start to express our program up in main, so that's where it is. So we say, okay, now we need to convert this code to Python. Well, then I would start to fill in the code in the main function. Okay, so look at what he's done. So he starts out using the conventions that he likes to use in the book. He has a comment that says what the name of the file is. He has a comment that states the intention of the program. And he's got a comment for the author. This isn't one thing that we're going to follow, especially in my course. You can always tell who the author is because the program inside of a project and a convention for the project name always includes the name of the student who's the author. So we're not going to need that. But he put the code into main. Okay, it had 3 parts. Okay, that's good. Is that too big for main? Do we need to factor some things out of it? Do we need to refactor this code? No, generally, somewhere between a half a page to a page of code is a good size. So if we're less than a half a page of code, we're well less than that in the main. That's probably fine. Okay? It's not too summarized, it's not too detailed. Okay, so how do these things work? Well, the first line is a combination of it's a combination of 3 operations. And I'm of 2 minds about this. One is my teacher mind says, gee, I wish we did this in 3 parts. Because I would like the students to kind of see this as 3 separate things that have gone on. Okay. On the other hand, the way this is done is very much the way Python programmers write their code. So the way that Python programmers write their code, would they say that the code that you write, it's like good Python programmers typically write, they call it Pythonic. It's Python-like, it's Pythonic. So this line here, to the learner, we're going to have to pick it apart. But the goal is to get you to be able to write things in this summarized of a way, because this is the Pythonic way. If you write codes like this, people would think you're a decent Python programmer. So how does this work? Well, this is an assignment statement, okay? An assignment this statement looks like algebra, okay? But that's just because it's following this kind of algebraic syntax that we favored in a lot of languages ever since the Fortran language. And what you might remember from chapter 1, we have a right-hand side. And so we evaluate the right-hand side, and then we get a value. We reduce it to some value. And the way that we interpret this equal sign is we call it an assignment. So we evaluate the right-hand side, we get a value, and then we place it in the variable name that's on the left-hand side. Okay. So what happens on the right-hand side? Well, it kind of works a little bit from the inside out. This input is a way of prompting the user at the console, kind of at the command line, to type in input. Okay, and it's a pretty complex. It's actually the name of a function. And what we do is we pass it the prompt. So the prompt is a string here, and you can see the author favors the double quotes. And so what we want Python to do is to prompt the user with the sentence, what is the Celsius temperature? Okay, and then wait for input. Well, what does input look like at the keyboard? Typically, one input will be the user typing a series of keys, and when they hit the return key, then the program reads that string that we typed in at the keyboard, and that's what input does. It reads that string. Well, what's this eval mean? So I said we start from the inside. So we prompt, then we do this input, okay? The input gets a string, it's typed at the keyboard, and what uses that? Well, the eval uses that. And eval, I think I mentioned this when we were talking about chapter 1. Eval, we're going to learn in the next of the chapters, is kind of an old-fashioned way. Actually, we're going to learn a little bit of this before we get out of this chapter. It's an old-style way of turning strings into numbers. So there's a difference in Python, as just about every computer language, between the character 3 and the number 3. Okay, so when we type at the keyboard, we're always typing characters. So when you do an input, what comes back? You get a character string. How can you turn that character string into a proper number to place into Celsius? Well, the easiest, most general way to do it, that is a bit old-fashioned, is to call the function eval. So eval expects to in our instance, the problem with eval and why its use is discouraged is that eval is a very powerful statement, too powerful, and it lends itself to hacking. Okay, but what eval will do in our case is it will take the string that gets returned by the function called input, and it will evaluate it and turn it into a number and put that into Celsius. Well, it'll just, eval will create the result, and then the equal sign, the assignment statement, will place it into Celsius. Okay? Now, what we're eventually going to do is we won't use eval. We'll use an instruction that turns a character string into an integer, or turns a character string into a floating point number. So we're going to use a substitute for eval that's not as hackable. Okay, so that's what happens in 1. 2, so that's input. A process is 9/5 times Celsius plus 32. The right-hand side is evaluated, and then the answer, the result, is placed in the left-hand side, Fahrenheit. Now, my complaint about this code is that it needs another set of parentheses. Okay, it needs a parentheses from the beginning left paren before the 9/5 and right paren after Celsius. Then it's clear that we're going to do the multiplication before the addition. And then we say print. So that's processing, okay? And then print is output. So we've done this before. We say, I think the only thing we've printed so far, well, we printed some numbers back in chapter 1. So we print a string, the temperature is, okay, and then a space, and then we have a comma, and then Fahrenheit, and then degrees Fahrenheit. So when we print and we give more than one argument to the print function, it just kind of goes down and it prints one, then the next, then the next. So the first one is a character string. Great. The second one is a variable that contains a number. Okay, so what's going to happen is implicitly it's going to get turned into a character string, and then it's going to be printed as a character string. And then degrees Fahrenheit is going to come out as a character string. Okay, so this was pretty cool because the mapping of our overall pattern of input, process, output, one line per. Okay, it's not always going to be that easy, but it's pretty good. All right. Now, once you write a program, you should test it. And they're showing this being tested in a Python interpreter console. And the problem that I have with that is that that's not what we use in my class. In my class, we're using PyCharm. So what we would do would be to run the program, and then it would pop up a command line console, and we'd be prompted what is the Celsius temperature there, and then we would put the answer in, and we would go from there. So let's see. The tests that they decided to do were Celsius of 0, and they get back 32. That's right. Then they do Celsius of 100, and they get back 212. And then they do the Celsius of -40, and the temperature is -40 Fahrenheit. And for people who have done the testing on this before, these are 3 key points. Okay, these are the ones that are kind of the easiest to calculate. So at -40, they come back exactly the same. At Celsius of 0, you've just got 32 Fahrenheit. And water boils at 212 Fahrenheit, which is 100 degrees Celsius, and that's not accidental. That's the way they scaled the scale of Celsius. Okay. All right, so there were a lot of things in there that we chose that we didn't really talk about too much, and now we're going to do a little play-by-play. So we had to pick names for things, right? So variables are typically lowercase, Celsius, Fahrenheit. If they are multiple words, instead of spaces, we use underscores. So the interpreter can tell that it's all one name. Okay, and then we've got modules. So the name of a module officially is the file that we're putting our code into. So we've got main and convert. Now These are actually the names of functions. So I think that's what we're talking about. Well, main is the name of a function, and converted is the name of the module overall. What all these names have in common is that they're called identifiers. There's identifiers that identify parts of the program. Every identifier must begin with a letter or underscore, followed by any sequence of letters, digits, or underscores. So you can't begin with a number. You can begin with a letter, okay? People who want to begin something that starts with a number typically begin with an underscore and then they have the number. So if they wanted to begin with a number 3, they just say underscore 3. Okay? Identifiers are case sensitive, which means that things that have a different case are considered different from each other. Okay? So typically, the names of variables and the names of functions are all lowercase, words separated by underscores. So these are all valid names, okay? The ones that are capitalized, by convention, the things that are capitalized in their initial letter are typically the names of classes, okay? Now, we haven't learned how to create a class, but we've used, I don't know if we've used a class yet, but we will soon. But so X would probably be the name of a class. Capital Celsius and capital Spam would be the name of a class. Lowercase spam would be the name of a variable or function. Mixed case spam would be legal but not really good conforming. Okay, this would not be an appropriate use of the rules. This doesn't break the rules of the language, it breaks the style guide. So in my class, we're using the PEP 8 style guide is automatically applied by PyCharm, and when you violate it, you see little squiggly gray lines underneath. So these mixed case things here do not break the rules of the language, but they really do break the style guide. So you probably would see some gray squiggly underlines in our PyCharm. Now, some identifiers are essentially built in. And so you can't just use any word at all, okay? And the other thing is that we do want the words to be meaningful and descriptive, okay? You'll see a lot of examples where people are using a single letter for things, kind of like they do in algebra, okay? But meaningful names for variables and functions and modules typically aren't like that. They're typically one or two words, 1 or 2 or 3 words. So you can't pitch this anyone. There's a list of reserved words. Okay, and here are some of the ones that are on the list. You can look on page 32 in your book, but and, del, for, is, raise, assert, elif, in, print. Not the word etc. That means itself here. Okay? And what's interesting is that there's even a couple of terms that haven't ever been implemented as a part of the language, but they didn't want, they've been used as parts of other languages, so they didn't want people putting that in there and confusing people. So the list of reserved words or keywords is actually longer than the list of words that are actually implemented as part of a language. Not by many. There may be 3 or 5, but they're there. Expressions we've already seen, okay? So, let's see. Expressions are the fragments of code that produce or calculate new data values. Okay, so we have arithmetic expressions. So we have those kind of formulas. They're a kind of expression. Okay, so what's inside of that arithmetic expression? Well, 2 things. One, simple identifiers. Okay, simple identifiers like variable names, like Celsius or Fahrenheit. And then literals. Now, literals are things that mean themselves, okay? The value itself. So if we have 2 kinds of literals. One are numeric literals, okay? So 3.9 is a literal. 1 is a literal. 1.0 is a literal. The other things that are literals are character strings, like hello. Okay? So the expressions that we have can be a combination of literal strings, literal numbers, functions, those kinds of things. And essentially, these expressions are evaluated. Okay, that's what eval you mean. That's what eval does. It runs the Python evaluation engine. And typically expressions are reduced to a single value. A number, a string. We have some other kinds of things. We have these things called booleans, true or false. So, but when you get done evaluating an expression, you have a single value. Okay? So for instance, here are some things that we can do. So this again is Python console. So we tell it that we want to assign the value 5 to x, and then if you simply in the console mode, right? If you simply type in the name of a variable, it will give you the value. So we typed in x, it says it's equal to 5. Well, that's what we thought. If we say print x, well, it tells us it's equal to 5. If we say print, and then we give it the name of a variable that we haven't defined yet, it's going to go nuts. So this whole traceback thing, this is kind of angry interpreter behavior when we've asked it to do something that is not reasonable. And what's not reasonable here? Well, we never told it what spam was. Okay? Name error. The name spam is not defined. Okay? Now, one of the things that's kind of interesting about Python, and it's different from some other kinds of computer languages, is that Python is kind of a lightweight, loosely typed language that allows us to. It's not real exacting about when we define our variables. Okay, in some languages, you have to pre-declare all your variables. You have to say what type they are and all this kind of stuff. And then later, if you try to use them, it looks up into the list of the definitions and said, is there a definition for that? Whereas Python, as an interpreted language and being a little bit less formal than some languages like, say, Java or Java or, say, COBOL or PL1 even, they it's not going to complain until you actually try to use it. So it's going to let you type in print spam, but it will. It's only really going to complain when you try to run it. And it's going to go, oh, well, I do that, but I don't know what spam is. We can combine expressions with operators, okay? And exactly what the combination operators depends on the kind of expressions. Okay, so you can take simpler expressions and you can combine them using operators. The plus, the minus, the asterisk, the slash, and the double asterisk. The double asterisk is exponentiation. The asterisk is multiplication. The slash is division. And plus and minus, you know well. Spaces are irrelevant within an expression. So the language is pretty tolerant of extra spaces in what you type. Now, your human readers aren't, okay? So there's like an ideal style for the number of spaces that you put inside of your expressions. If you just jumble everything together, perhaps the interpreter can understand it, but your readers who come after you will have a hard time scanning the line and reading the line. For instance, we could take, if you look at this last expression here, there's a space before the plus and one after. We could get rid of those. There looks like there's a space before the slash and one after. We could get rid of those. The interpreter wouldn't care. The human reader, however, would have a difficult time reading the one that's really scrunched up. Okay. So the normal mathematical precedence applies, which is essentially things like addition and subtraction are weaker than multiplication and division, and that of things that are of equal weight, we go from left to right. I prefer, and I'm going to really hold you to it in this class, that you put enough parentheses into your expressions that we don't have to resort to consulting the precedence of operators. Output statements. So we can say print paren paren. So when we print, it's a call to a function. And the paren paren is where we would put the arguments to the function. And if we just want to print a blank line, we just don't put any arguments in. So print paren paren, blank line. Or we can say print and any number of expressions after that. And what it's going to do is it's going to do the first, and then it's going to add on the next, and then it's going to add on the next, and then it's going to add on the next. So a print statement can print any number of expressions. The successive print statements will display on separate lines. So this first one is a print statement. This second one is a print statement. Okay, so if we have one print statement like we do here on the second one, and it has 3 or 4 or 8 expressions, they'll come out in series one after the other, but they will not get a new line. So you have to get a whole new print statement to get a new line. There's some other tricks to get a new line, but that's what you need. A bare print, that's this one up top, will print a blank line. Okay. So there's a couple of interesting things here, okay? If we we just have an expression. So we've got 3 and 4, they're numeric literals, they're connected by a plus, that makes it an expression. Python's just going to evaluate that expression, it adds it to it, gets a 7, and it prints it out here. If we print 3, if we have 3 things to print, a 3, a 4, and a 3 plus 4, we're going to get a 3, a 4, and a 7. Now, one of the things that's kind of interesting is that it put a space in between these to make them easy to read. Okay, so we can go ahead and print a series of numbers like that, and still they're pretty readable because we got that separating space for free. We didn't explicitly ask for it anywhere. It's just a feature of the language. We get a bare print, nothing, but a blank line. 3, 4, and then an end expression. Now let's, okay, this is a cool feature. Normally, when we call the print function, we're telling it to print all the things that are on that line, okay? And the last thing implicitly is a new line. So on typical computers, that's a control plus new line plus a line feed. But that's how we get the new line, okay? So the default is like up at the top, add 3 plus 4 together and print it, and then do a new line. So that's what we got. Here, the next one, 3, 4, and 3 plus 4, implicitly a new line. Print, there's nothing here, but you get a new line. Now, if you want to end with something other than a new line, like a space, well, you won't get a new line. So when you end with a space, then you don't get it on that line. The next time you print and you implicitly get a new line, you get it there. So here what's interesting is that the 3 and the 4 are coming from up here. The space after the 4 is coming from what the space we have is an end equals space, and then the 7 is coming from print 3 plus 4. Okay, and there are times when we want to use more than one print statement, but we only want to get one print line. So this end equals space is a way to do that. If we say print and then a character string, a comma, and then a numeric expression, note that even though we don't have a space after the word is, okay, we do get a space here. So we're getting a space before that 7, even though we didn't explicitly ask for it. Now there are a lot of languages in which that wouldn't work. That wouldn't work in the Java language, for instance. Okay. Okay, assignment statements. So assignment statements look like algebra. Okay. They're not algebra. Okay. It's just an algebraic style of saying I want to move what's on the right to what's on the left. Okay. So we talk about the right-hand side, RHS, and the left-hand side. So the right-hand side could be a single value. Okay. It could be a literal value. It could be an expression. Okay. It could be a variable name. Okay. The left-hand side is almost always a variable name. It's always a variable name. It's a place to put it. So what happens is Python evaluates the right-hand side, and the result of evaluating an expression is always one value, of some type or other. And then the equal sign, that single equal, is assignment. Then it moves the result over to the left-hand side, to the variable name that's in the left-hand side. Typically, we don't have expressions on the left-hand side. The expressions are on the right-hand side. Okay? Now, there are quite a few computer languages that have programming languages that have assignment statements for the way that you move data. One of the early languages that I learned, COBOL, it was more English, like you would say, move expression to variable name, or yeah, you'd say move variable name to variable name. But so this kind of algebraic way of expressing moves wasn't used in good old COBOL. But this equal sign as an assignment statement, again, it's been around for a long time. It's been around for 40, 50 years in languages, and it's just really popular. So here's some examples. So we take 3.9 times x times 1 minus x, and we get that answer. Hopefully we know what the value of x is when we start. Okay, and then we plunk the answer into x. And I just want to point out here that this is a typical programming trick, okay? One of the reasons that we know one of the reasons I want to assume that this is an algebra, okay, is that we're not saying that at any given time that x is equal to 3.9 times itself times 1 minus itself. What happens is that these things are true in two different time frames. The right-hand side is true when you begin to execute this statement, okay? So we use the value of x when we begin to execute this statement. What happens is that we get some value, and then we assign that into x. Well, that gives a new value to x. So certainly we're not claiming that at one instant in time that this, what looks like an algebraic claim, is true. Okay, so the x on the right-hand side is kind of like x when we started to evaluate the statement, and the x on the left-hand side is the value that x will take on when the statement is completely executed. And quite often they're different values, right? This is a typical trick. So we can have, the one thing that we're not showing here is we might say x equal Celsius. And we might just assign or move the value from one variable to another variable. And again, I just want to emphasize that the name of x for a variable name is pretty crummy, okay? Because even though that's a tradition in algebra, to use x and y and z and a plus b plus c and all those kinds of things, in programming it's not. Programmers are judged by having variable names that are short enough that they're not hard to type or hard to read, but long enough that they're meaningful to the casual reader. Okay, so Fahrenheit, I think that's great. Celsius, I think that's great. Now, could you say temperature in Fahrenheit? and separate the words with underscores? Yeah, you could. Temperature in Celsius, I think you could. Problem is that that's sort of implicit, and temperature in Fahrenheit and temperature in Celsius are kind of wordy. Now, would I hold it against you if you did it? No, I wouldn't. Would I expect you to be that wordy? No, that's maybe a little more wordy than I would expect. Okay? When we're working with formulas like this, they're pretty easy to understand because we learned how to do this in, I don't know, 4th grade. You probably learn it in kindergarten now, but I think I learned this in 4th grade. Then we can be a little more shorthanded, but I wouldn't use, for Fahrenheit, I don't want to see you using F or Fair, okay? Type out Fahrenheit. And for Celsius, I don't want you using C or Cell or Cells. Type out Celsius, okay? So there's a happy medium in terms of how verbose your variable names should be. And I think that both Fahrenheit and Celsius are right in the sweet spot of that. Okay, we're not going to the next slide. Let's get there. Variable names can be reused. Okay, they don't get tired. So you can think of a variable name as a label that's given to a value. Okay, and you can here we can move a 0, and we can associate with the name myvar, and we see that. Then we can reuse it and give it a 7. Okay, and then we can say we can have one of these where we use myvar on the left side, and then we give it a new value. Myvar on the right side, and we give it a new value on the left. So it starts as a 7 and it ends as 8. All pretty typical things. Having a hard time getting to this next slide. So here we are. Variables are like a box we can put values in. And in more traditional programming languages, this is exactly what they are. A variable name in traditional programming languages is associated with some part of the memory of the computer, of the RAM. And when you move a value to that variable name, it goes in a particular spot. Okay? Python, being very object-oriented, is not that simple. Okay? You can think of it that way, but what we're going to do is we're going to show you a way to think of it that's a little more complex, but more realistically what goes on. So if we think of it like a box, okay, we have the box, the area of the memory associated with the name X. And before we execute this statement, the value in X is a 10, and then we have X equals X plus 1. And some people are so, I just want to point this out, if some people want to be so warning that this is an algebra, that some people will say something like, they'll read this line, X is assigned X plus 1. So we call it an assignment statement. Many of us, including me, will read it as equals when we're reading a program, okay, out loud. But some people would say X is assigned X plus 1. Because it's actually a more appropriate, more legalistic reading of what's going on. So if the value of X before we execute that statement is 10, then the value after is 11. Okay? So that's how you think of this in terms of variables having a piece of storage, a piece of memory associated with them that's that's a box. It's in a particular place. Okay, now the reality in Python is a little more complex, and that is values are what hold a piece of storage. Okay? And variables are associated with values. Okay? So, before we execute that line, the variable x is pointing to the value 10. Okay? After we execute that line of code, the variable x is pointing to the value 11. Well, what happened to the value 10? Well, the value 10 is going to hang around for a while. These kind of object-oriented languages have this feature called garbage collection. And it works like this. Every once in a while, the Python interpreter, the Python environment will say, I want to make sure we're not wasting a lot of memory. Let's look around and see if there are any objects, any values that are not being pointed to by any variables. And they go, okay, 11's okay, that's being pointed to, but there's nothing pointing to 10. And so it deletes it. It gets rid of the object, it garbage collects it, and it frees up the memory. So for right now, in terms of these values, you can think of it in a more a traditional kind of way. This was true like for the language C and for the language COBOL and the language Fortran. But in Python, which is much more object-oriented, the fact is that you could think of the variable x as having a box, but it's got a pointer to some value object. Okay? And you can think of the value objects all being, kind of glommed around in the memory, and every once in a while, a garbage collection is going to run and get rid of all the values that are not being used. And how do you know if they're not being used? Well, if no variable is pointing to them, the program can't really use them anymore. They really are garbage. Okay? It's called garbage collection. Okay, assigning input. So it's not accidental that the first pattern that we taught you was input, process, output, because that's kind of what computers do. Okay? When they're highly interactive and we're doing a lot with them, like the typical interaction you'd have with your smartphone, well then we don't really think of it that much that way. We think of, we have an ongoing conversation with the application, but isn't a conversation with our smartphone just a continuing series of input, process, output interactions? Okay, we touch the screen, that's an input. It does some processing. It changes the look of the interface. It puts some value there. It switches screens. That's the output. Okay. So the purpose of an input statement is to get input from the user and store it into a variable. It's kind of interesting. We say store it into a variable, but what is really happening is we get a value and we point the variable name to it, don't we? See, it's hard to get around that way of talking about what variables are. So these right-hand side expressions are typically evaluated from the inside out. So the first thing we're doing is we're going to prompt. We're going to put out a prompt string. And then the next thing happen is we're going to wait for input. And that input is going to get us back a character string. And then we can evaluate that. Typically that means turning it into a number. And then we're going to assign that number to a variable. And when we say a number, that number is a value. It's an integer 10. It's a floating point 3.159. And what happens when we assign it? Well, we can think of it, we plunk that value into whatever that variable is, but really we're just pointing the variable at that value object. Okay? So here eval is wrapped around the input function. This is a typical thing to do. A lot of times when we're getting input, we want numerical input, okay? And again, there's a big difference between the kind of things we type on the keyboard, which are characters, which when you aggregate them are character strings, and those values are not computable. You can't do arithmetic. So if you have a character 1 1, that's not the same as having an 11 until you do something to turn it from a character into a number. And the simplest way to do that is with evaluate. In the next chapter, we're going to talk you out of evaluate. We're going to say turn this into an integer value, or we're going to say turn this into a float value. Okay, so we're going to be learning how to do that in the next chapter. Assigning input. So first the prompt is printed. The input part waits for the user to enter a value and type in a value and press enter. The expression that was entered is evaluated to turn it from a string of characters into a Python value. The value is assigned to the variable. Okay, just what I said. Now, beware, the eval function is hackable. Okay, the eval function is you're allowed to type in any valid Python. So you could type in something that said, oh, you wanted to save the program, you wanted to delete the program. I mean, just any valid Python will work there. And in theory, the Python interpreter will just go do it. Well, that's a hacker's dream. Okay? Typically, when we have a statement like the one we just saw, or let's go back one, when we have one like this, we know what kind of value we're looking for. So we have functions equivalent of eval. We have one that will take a character string and turn it into an integer value, an int value. We have one that will turn it into a floating point value, a float value. So it's the same kind of transformation, but it's more specific and it's much less hackable. Okay, so we left this eval into chapters 1 and 2, but starting in chapter 3, we're not going to let you use it anymore, because despite what the author says here about not so much of a problem when you're only creating programs for yourself, who knows who's going to use your program someday. Okay, so we're going to say that using eval is a bad practice. Okay, it's a good sort of a learning crutch for chapters 1 and 2, but by chapter 3 we're already going to have discarded it. This kind of hacking is called a code injection attack. So our code, the way we wrote it, is expecting you to type in a number. We told you to type in a number, okay? But the code that we actually put there, it'll process all kinds of evil commands, evil. You can call functions, you can do whatever you want. You could put a whole program in there. There's nothing to keep you from doing that, okay? And putting in code to execute, that's a classic hacking approach. It's called code injection. So that's why we're going to give up on eval after chapter 2. And I would say to give up on it even for programs for your own use. It's just, we're going to say it's just not a good practice to use eval. Simultaneous assignment. So several values can be calculated at the same time. Okay, so what we have here is we have the variables that the expressions are going to be evaluated and assigned, and we can have two outputs, variable 1 and variable 2, and then two expressions of variable 1 and variable 2. And of course, we could have 3, we could have 8, we could have whatever. This is a feature of Python that, coming to Python late in life, I'm not a big fan of. Okay, there are some operations that you can do, okay, that will throw off more than one value. And I think if we're doing something on the right hand side, some one coordinated action that throws off more than one value, then I think a statement that's got more than one variable name on the left, it's a really good way to document that. You look at it and you go, oh, this work throws off two values, or it throws off 4 values. But as a way of saving space, this is, I don't think, a good thing to do. Okay. Call me a fuddy-duddy. We do see one trick here that you can use it for, but so here we go. We've got two variables, one called sum and one called diff. And so we have an expression that sums them, an expression that diffs them. Okay. But could we have done this on 2 lines? Absolutely. Would it have been better on 2 lines? For me, it would have been better on 2 lines. Okay. Will I hold it against you if you put it on 2 lines, on 1 line? No, I probably won't. But again, be careful the code that you leave behind, because the person who has to maintain it may be you. I'm pretty much a sole practitioner in my programming, and I come across the code that that I wrote a year and 2 and 5 and 10 years ago, and it's new to me now, and I have to read it like any new person. So this trick where we do this thing in 1 line instead of 2, for me that's just potential confusion, so I don't really like this. Now, what else could this be good for? Well, I told you if we have some operation on the right hand side that throws off more than one value, and that's a couple of chapters away. Okay, but what about if we wanted to exchange values? Okay, now when you really think about this, this is just one case. If you're exchanging values, then you're throwing off 2 in the order matters, right? So we could use a temporary variable. So we could do something like this. We have x is 3, y is 4, print xy, xy equals, gets assigned yx, print that is equal to 4, 3. So you could in fact write a sequence of code in which we created a z to hold one value temporarily, and we could explicitly move them. Okay, but this is a way to swap them without having to explain where you're going to put the temporary variable to keep from losing one of the values when you move the first one. So yeah, this is a thing that throws off 2 variables. This is kind of the trivial case of it. So I like this. Having a hard time getting to the next slide. We can use the same idea to input multiple variables from a single input statement. Use commas to separate the inputs. Okay, so we could say that we want to get spam and eggs, and it says enter number of slices of spam followed by number of eggs. Okay, so then you would put in two values, and then it would know which was spam and which was eggs. Now, is that a good user interaction style? Well, for me, maybe not. Okay. But that's okay. It's an interesting feature. So what is happening is this eval is expected to throw off two values. That's all that's going on. Okay. Again, in my interactions with the user, can I ask them for two things at the same time? If they're related. Okay. Let's say we're saying this. I'm drawing boxes for you. Okay. And I say, give me the dimensions of the box in inches. So 3 and 10. So I put in 3, 10, and one is the height and the other is the width or whatever. Yeah, I think that makes sense. But 2 slices of eggs and 3 slices of spam, 2 eggs and 3 slices of spam, that's good. But what about toast? How many slices of toast do you want? And do you want orange juice? And do you want coffee? Okay. How many things are we going to put on this line? Okay. I'm getting hungry just talking about it. But again, you can put more than one variable on the left side separated by commas if you're throwing off more than one on the right side. And some functions like input can return more than one value. Okay. Golly, we're having a hard time. Let's see if we can get to 39. There it is. So loops. We talked about loops in chapter 1, and we did one in that chaos program. And people in my class, we also did one for our homework exercises. So we've seen one before, and we're going to go over the more general points of it. So this is a definite loop in that it happens a fixed number of times. Okay? If we had an indefinite loop, that would be a loop then maybe we're going to loop around until they told us to stop by giving us some kind of special value, often called a sentinel value in a sentinel loop. Well, this is more simple than that. It's going to go 10 times or 4 times. Okay? And each time around the loop is called an iteration, a repetition, an iteration. And we have this kind of header in which we have information from which you can determine how many times we're going to go around and what values we're going to use. And then we have the body, which is the work of the loop. Now, we're showing it here as just one expression, but typically it's a sequence of statements. Okay? And how do we know what the body is? Well, it's indented. And people often ask, well, how much do we indent? Well, we typically indent 4 spaces in well-styled Python. In PyCharm, which is the IDE which we're using in my class, PyCharm is set up so you can use a tab and it will turn it into 4 spaces for you. So we're using 4 spaces in my class, although the students who are using this product might only be pressing the tab key. Okay, so The variable after the 4 is called the loop index. Sometimes I call it the control variable. I know I used that in the lecture for chapter 1. It takes on each successive value of in the sequence. So this last part, the sequence, this is some variable or expression that's going to give you a sequence of things. Okay? And what's going to happen is every time we go through the body, the first time we're going to get the first one in the sequence, then the next one, then the next one, then the next one, then the next one. Okay? Often the sequence portion consists of a list of values. So one of the kind of sequences that we have in Python is a list. Okay? So what does a list look like? Syntax-wise? Well, it's a sequence of expressions in square brackets. Let's see that. Well, do we have one? Yeah, we went the wrong way. Oh, here. Okay, so here for I is the control variable, as I like to call it. What was the official name? The index variable? I think it is. Loop index. That's what he calls it. I call this the control variable. Okay, so what's going to happen here is that we have a list of the values 0, 1, 2, and 3. They're not in quotes or apostrophes, so it looks like they're number values. They're numeric literals, they're integers. So it's integer 0, 1, 2, 3. So the first time we do the body, I is going to be equal to 0. And then we're going to go around and do the body again. I is equal to 1. Do it again. I is equal to 2. Do it again. I is equal to 3. Okay? And from this, you could predict that the output would be 0, 1, 2, 3. And that's what happened. Okay? So here we say for odd in 1, 3, 5, 7. So odd, what I like about odd is that this is a variable name that's a little more descriptive than the classic I as the index of a loop. And it's to call attention to the fact that the values in the list are odd integers. So for odd in 1, 3, 5, 7, print odd times odd. So we're going to get odd squared. So I would expect to get 1, 9, 25, 49. And we get 1, 9, 25, 49. And so this idea that when we test by inspection, that we predict ahead of time what our what the outputs will be, and then we go and compare what our actual outputs were to our predicted outputs. Here, that's all pretty straightforward, but in some programs, that's going to be much more challenging. Okay, so back in chaos.py, we used an expression for the sequence range 10. And I talked about this in, not so much in the lecture, but in the tutorial. Range 10 is a way to generate a list of 10 values. Okay, the surprising thing is it starts with 0 and ends with 9. And this just has to do with the way counting goes on in Python, and most things, counting of things begins at 0. So if we count 10 things, it's going to be 0 through 9. Okay? Now what's a list? Well, a list is a data structure that we're going to learn a lot more about in a subsequent chapter that holds sequences. Okay, and how do we create them in Python syntax? Well, we begin with a square bracket, and then each of the members of the list are listed, and then the end of the list is a closing square bracket. So when we say that we want to take range 10 and convert it to a list, then what does that look like? Well, it looks like that. Okay. For loops. Now, for loops alter the flow of the program execution, so they are referred to as control structures. So there aren't a lot of structures in programming. One that we've seen before is just called the sequence. Okay. We do statement 1, 2, 3, 4, 5, 6, 7. Okay, so that's the simplest structure that we have. Okay. Now, how do we get more interesting flow of execution? Well, one control structure that we can use is a for loop. Okay. And there are other kinds of loops, and there are if then else's we're going to learn about. So we'll learn about a lot of things. So what's this thing on the right? Well, this is programmer flowcharting language. Okay. And back when I learned how to program, one of the things that you learned before you learned how to write the code was flowcharting language, because people thought that the visual expression of the algorithm was more clear, more easily understood than the textual one. Okay, so what's a diamond? A diamond is a test. What is a rectangle? A rectangle is a just one statement. Okay, so what do? We come in, we test. On the basis of the test, we either go to the next statement, and then the one after that, and then we go around to the top. Or if we have another outcome, then we go down after the structure. So for loops are a test before control structure. So you can think of the test as happening before we ever do the body. So for loops can be executed 0 times. Okay, so if we said for I in and we gave it an empty list, it would say, oh, well, I'm done. Do I have more items in the sequence? No, I don't. I'm done. If I do have another item in the sequence, well, then I do the body. Oh, the control variable equals the next item in the list, and then we do the body. Okay? Now, why don't we emphasize programming logic using programmer flowcharts more than we do? Back when I got into programming, which was 40 years ago plus, we eventually gave up on this because you could draw things that we didn't consider to be good practice. Okay? So for the most part, we use them as a way of explaining things that we've otherwise designed out of approved parts. But one could diagram program designs that were not well chosen. Okay? So again, we use programmer flowcharting typically as an explanation aid, and as a design aid, it's really been replaced by pseudocode. Okay, so we have some kind of a word expression of the problem, and then pseudocode, and then right to the language itself, Python. And we would use diagrams like this to make the logic more clear after the fact. Okay, so now we've got one more example program to go through, and I want to emphasize the fact that one of the reasons why the author picks these mathematical examples is there are two. When you're teaching, you always want to pick things where you don't have to teach people new things about the world. Okay. And so, you either pick some you pick a simple problem that everybody understands. Well, and also these computer science professors, they were math majors, so they love math. Okay. Now, future value is a concept that I like. You may have already used this. There are a whole series of calculations that have to do with time value of money. Okay, and if you've ever had to borrow money, or if you've ever put money into a bank account or investment in anticipation of getting more back later, knowing the formulas and how to do them, it's pretty interesting to do. If you have a word problem that says, well, if you have a certain amount of money now and you put it in a savings account for so long, how much will you get back? Well, that's probably something that you want to know because you want to do something with it, right? And do you really want to calculate that by hand over and over again? No, it'd be really nice to put together a calculator program. So most financial calculators have a future value button. So you put in this, and you put in one input, you put in another input, you put in a third input, and then you press the calculate future value button, and you get the answer right in the window. And most spreadsheet programs have a function for future value too. Okay. Now, you're probably only so interested in being able to write the code for that, but I could see that you might have to write the code for that. So what we're doing is this is the time value of money. So the money deposited in the bank account earns interest. How much will it be worth 10 years from now? So the inputs are the principal and the interest rate. Okay. The output is the value of the investment in 10 years. Now, I just want to cheat ahead here and say, for me, this is a program that only calculates what the value of the money would be in 10 years is not very general, because sometimes you want to know 10, but then you go, oh, well, maybe I can leave in there a little bit longer. What will it be like in 15 years? Well, no, we don't have that program. Okay. So I would have had the inputs be the principal, the interest rate, and the number of years. Okay. And I wouldn't have this program be so specific as the current design. But I think that's an improvement that we got in a future chapter. And the output is the value of the investment in 10 years. Okay? Why don't we have a really succinct expression of the processing? Well, it's a little harder than we can put into one bullet. Okay, so in KS to Pi we had ranges. We had range of 10. And if you want to put those into a list, you can have a list of range of 10. It can do that. Sorry about that. Oh, I went the wrong way. I'm having a hard time with my monitor today. So specification, that's the way I was supposed to go. The user enters the initial amount to invest, also called the principal. User enters an annual percentage rate, the interest. The specifications can be represented like this. blank, blank, blank. Okay. Don't know why it keeps going back to number 42, but it wants to. Okay, so this looks like a program specification. Okay, we have a name for the program, future value. Now that capitalization's not proper for Python. We're going to have to see how that goes. How many inputs does it have? Well, 2. The principal, the amount of money invested in dollars. Okay, so that's going to be, it's potentially going to be something that includes a decimal point. Okay. An average percentage rate, the annual percentage rate expressed as a decimal number. So 10% would be 0.10, 5% would be 0.05. The output is the value of the investment 10 years in the future. And what's the relationship? The value after 1 year is given by the formula principal times 1 plus the annual percentage rate. This needs to be done 10 times. Okay, so we could do that with a loop that went around 10 times. All right. It went back to 42. My, am I having a hard time? Apologize for that. So I'm going to have to use my scroll wheel. I promise I will. Okay, so here's the design, and now this is looking pretty pseudocodey. Okay, print an introduction. Input the amount of the principal. Input the annual percentage rate. And then in parens, I guess these are the names that we're going to call the variables. Repeat 10 times. So this is a pseudocode way of saying we're going to have a fixed loop. Okay, a deterministic fixed loop. And we're saying that principal, that's the amount that our money's currently worth, is equal to the starting principal times 1 plus the annual percentage rate. Okay, so we go around there 10 times. So you could go down the first time, and then you've got the principal value at the end of 1 year. And then the 10th time, you're going to have at the end of the 10th year. And then we output the value of the principal. Okay, that makes sense. So each line, the implementation, it turns out that the correspondence between pseudocode and Python here is going to be line for line. Is that always true? No, sometimes it's a little more summarized than that. Okay. So let's see, print an introduction. Well, this turned into 2 prints. Okay, we wanted it on 2 lines for some reason. Just to prove it wasn't going to be line for line, I guess. Input the amount of the principal. Okay. So again, I've warned you that starting in the next chapter, we're giving up on this hackable eval. Okay. In the next chapter, we would use a function called float. That would get us a floating point decimal number. Okay. But here we use the old style eval. And inside of that is input, and then inside of that is the character string. Enter the initial principal. Okay. And then the next one, input the annual percentage rate. And then we say repeat 10 times. That turns into for I in range 10. Okay. Now, one of the interesting things here, I just want to point this out, is you remember back when we talked about chaos.py that range 10, it generates a sequence of 0 through 9. Okay? If in fact we wanted to use the value of each of the members of the list that we generate from that, if we wanted to use those values in the calculation, it might be a problem that we're getting 0 through 9 rather than 1 through 10. If we wanted to print them out, it would be a problem. If we wanted to print out 1 through 10 and we printed out 0 through 9, we'd be disappointed. I just want to say that here, the only thing that we're trying to do is to control that we do this 10 times. We never use the value of I in our calculation. There are no i's in here. So this, for I in range 10, is only there to make sure it goes around 10 times. And I is not used in the calculation. If it was, we might be a little bit more careful about this expression that generates the list that we're going to iterate over. Okay? So this is the calculation, and then we print the answer. So let's go to 50. Here's the program. And again, everything is pretty much as we described. He's gone to not saying file future val but .py. He just has that there as a comment. He's got 2 comment lines to describe the intent of the program. Again, comments are either giving some important detail. One of the things that they're good for is stating intent. So this is, I think, a pretty good comment. Okay, when they begin to start to state the play-by-play that's coming, then you get both the action and the play-by-play. Probably better to just have the action. Okay, unless the action is really hard to follow, then some commenting about the play-by-play is appropriate. And there's our program, and then we run it. So we say enter the initial principal, 100, I guess that's $100. Enter the annual interest rate, 0.03, that's 3% per year. That would be a big interest rate in today's savings account world, where they're closer to 1. In 10 years, it'd be $134 and some cents. So if it was 1% interest, it would be really low, which is the reason why nobody's saving. But if the interest rate were 10%, it'd be pretty high, $259.37. Okay, so this calculator program, this is another classic program kind of style. Okay, and what's really nice is it fits right into that input process output. So when you think about it, the Celsius to Fahrenheit is a calculator program. The future value is a calculator program, and they both fit really nicely into this initial pattern that we're learning about called input process output. So that's it for the lecture. For those of you in my class, we're gonna be doing some programs that are using all the skills that we learned in the chapter, and I'll have my tutorials up for those soon. And I'm just going to say bye until next time. Bye-bye.